예, 안녕하십니까. 오후 첫 번째 세션 이제 풍력 수소 관련해서 진행된 세션의 좌장을 맡은 한국에너지기술연구원의 정치영입니다. 예, 오후 세션은 이제 플래너리 톡 한 세션 하고요. 그다음에 풍력 쪽 발표 2개, 수소 쪽 발표 2건이 이제 예정되어져 있고요. 먼저 플래너리 톡 관련해 가지고 이제 한국전기연의 김종률 본부장님께서 탄소 중립 달성을 위한 가상 발전소 기술 발표를 맡아 주시겠습니다.
네, 안녕하세요. 조금 전에 소개를 받은 한국전기연구원 김종률입니다. 반갑습니다. 네, 아직 본부장은 못 됐고요. 에너지 플랫폼 연구센터를 지금 맡아서 맡고 있습니다. 제가 오늘 말씀드릴 거는요. 저희는 이제 전기연구원이고 제가 근무하는 곳이 이제 스마트 그리드 연구 본부 내에 저희가 이제 근무를 하고 있는데요. 그래서 어쨌든 우리나라 스마트 그리드와 관련된 기술 개발 연구를 하고 있고, 그래서 저는 이제 그 관점에서 이제 오늘의 좀 주제를 스마트 그리드 중에서도 좀 재생에너지와 밀접하게 좀 관련이 있는 부분이 사실은 가상 발전소이기 때문에 가상 발전소가 왜 필요한지, 그리고 가상 발전소는 뭔지, 그리고 또 가상 발전소가 뭐 오늘 주제와는 약간 다르지만 이제 사실은 가상 발전소가 AI가 데이터 센터가 들어오고 거기 데이터 센터에서 쓰는 전기를 공급하는 데 기여도 하지만, 또 역시 가상 발전소가 운영을 잘 하려면 또 AI의 도움을 받아야 됩니다. 그래서 그런 어떤 상관관계가 있는 기술이고, 그래서 그 관점에 대해서도 마지막에 조금 간단하게 말씀을 드리도록 하겠습니다. 네, 이제 마지막입니다. 뭐 앞에서 말씀드렸던 겁니다. 이제 가상 발전소는 말씀드린 것처럼 재생에너지를 많이 수용하기 위해서는 무조건 필요한 기술입니다. 가상 발전소가 재생에너지를 잘 컨트롤하고 관리하고 모니터링 해주기 때문에 그래야만 재생에너지를 전력망에 많이 수용할 수 있다. 그렇게 이해해 주시면 될 것 같고, 그런데 이제 가상 발전소가 해야 되는 요구 기술의 수준, 그다음에 다뤄야 되는 자원, 이런 것들이 너무 버라이어티해지기 때문에 이제 그거를 다루기 위한 에너지 플랫폼도 굉장히 고도화돼야 되는데, 그 고도화할 수 있는 대표적인 방법이 AI를 굉장히 적극적으로 활용을 해야 된다. 그 두 가지가 어떤 서머리가 된다고 말씀을 드릴 수 있겠습니다. 자, 이상으로 제 발표를 마치도록 하겠습니다. 감사합니다.
안녕하십니까. 저는 DMV의 문영희라고 합니다. 초대 강연에 저장을 맡게 됐고요. 지금 군산대학교 풍력에너지학과의 이상일 교수님께서 해상 풍력의 현황과 전망에 대해서 발표를 해주시겠습니다. 박수와 함께 모시겠습니다.
예, 반갑습니다. 한국풍력에너지학회 회장 이상일입니다. 저는 지금 현재 군산대학교에서 근무하고 있고요. 풍력에 관련된 이야기를 이렇게 발표해달라고 제안을 받았을 때 어떤 말씀을 드릴까 고민하다가 아무래도 지금 분위기상 신재생 에너지가 갈 것 같고, 그리고 해상풍력 쪽으로 아마 정부가 드라이빙을 많이 거는 것 같아서 이 부분의 현황하고 앞으로 어떻게 될 것인가에 저의 전망입니다. 국가의 전망이 아니라 제가 보는 견해에서의 전망을 말씀드리는 게 좋을 것 같아서 그렇게 주제를 정했습니다. 그 다음에 최근에 이슈가 되고 있는 LCOE, 물론 이 발전 단가가 누구나 다 관심이 있는 거긴 합니다. 근데 우리나라는 해상풍력만 보면 아직도 갈 길이 멉니다. 다른 나라에 비하면 훨씬 비싼 편인데요. 근데 이거는 아시겠지만 카펙스, 오펙스, 피넥스 세 개가 이렇게 합사해서 계산되는 거죠. 근데 우리나라 같은 경우는 아직까지 저의 견해입니다. 아직까지 안 돼 있던 거는 공급망 문제라고 생각합니다. 그래서 독일 예를 들면 독일이 풍력의 메가와트 수가 설치 용량이 증가하면서 특정 구간에 와서 LCOE가 내려옵니다. 이게 공급망 체계가 완성되었을 때입니다. 그래서 우리도 만약에 공급망 체계가 국산이든 외산이든 공급망 체계만 완성된다면 LCOE는 좀 되지 않을까, 해결하지 않을까라는 생각을 해봅니다. 이상으로 제 발표를 마치도록 하겠습니다. 감사합니다.
네, 다음 발표는 일본 도호쿠 대학의 가와타 타치야 교수님께서 일본의 수소 생산 및 혈연 기술 개발 현황과 고온 고체 산화물 기술의 향후 전망에 대해서 발표해 주시겠습니다.
Okay, my name is Tatsuya Kawada from Tohoku University, Japan. Thank you very much for inviting me to this nice symposium. I have some difficulty in understanding, but that panel or that translation works very well. So thank you very much. And today I'd like to present about the development status of hydrogen production in Japan and future prospects of high temperature solid oxide technologies, because I'm mainly working on solid oxide fuel cell and solid oxide electrolysis cell, that is high temperature technologies. So the content includes some rough introduction about the present status of hydrogen generation in Japan. But I'm not from the government, so I do not know exactly about the situation, all the situations. So I will just introduce some governmental projects in some slides, and then go to the high temperature solid oxide technologies, and I will explain what are SOFC and SOEC, and why do we choose that technologies. And then go to the history of the SOFC development and the current status. And if I have more time, then I will add some slides about our recent activities in the university. So this is Japan's outlook of the energy supply and demand for future, and present and future. So this is the prospect is not very challenging or rather conservative target, but we are trying to increase the renewable energies. This green part is the renewable energies. So still, I think it is too conservative, but anyway. And the energy-related project has been handled by NEDO, that is a new energy and industrial technology development organization that handles all the budget or projects done by METI, Ministry of something, MEA. I forgot the name, but METI is the abbreviation. So from that budget, NEDO is doing the work to deliver those budgets mainly. So now about the fuel cells and hydrogen, they have 4 kinds of the projects. The total for the first project, that is technologies for realizing hydrogen society, and the second one is hydrogen refueling stations, and the third one is competitive hydrogen supply chain. So it is very difficult to understand the difference, but anyway, they have this amount of the budget, 8.1 billion yen or 80 billion yen or 6.4 billion yen for those projects. And the last one, that is the common development of the common platform supporting the widespread use of hydrogen. That is for more, for academias, universities and institutions have some budget from this project. That is 7.2 billion yen for this fiscal year. And in that project, there are several items, and our SOEC activities is also included in here. Only 0.4 billion yen per year for 1, 2, 3, 4, 5, 6, these universities and one institutions, AIST, and also Central Research Institute for Electric Power Industries. So those are together have the 0.4 billion yen per year. I hope that will be getting more and more next year. Anyway, this is the main kind of the support from the government, and also recently government provides the some bigger budget project that is called the Green Innovation Fund project. So they have very large fund for many kinds of the projects. And for hydrogen related projects, we have these 4 technologies. One is a large-scale hydrogen supply chain establishment, and they are building a hydrogen transportation ship. So actually, recently, it is to that we expect to import hydrogen from Australia, but recently, maybe you know, Australian government stops the subsidy for the making hydrogen from their coal. So it is they have some difficulties, but anyway, we have large amount of budget for spending for here, and also hydrogen production through water electrolysis has the budget of 72 billion yen per for this project for this year. And this is for the companies who is developing hydrogen production electrolyzers. So recently, the government decided that the SOEC is also included in this support. And other things, hydrogen utilization and iron steel making process, and ammonia supply chain establishment. And also CO2 carbon project is also related to the hydrogen, because if you have hydrogen, then Sabatier reaction can use CO2 to make the syngas, CO, and also we can have the we can reduce the hydrogen CO2 to utilize it as the carbon source for energy and for products. And in that, we also SOEC project is also included in this development of technology for producing fuel using CO2. So we are some companies are making the methane, so through the methanation reactions after the electrolysis of CO2 and water using high temperature fuel electrolyzers. That is, we call co-electrolysis technologies. And also other companies are doing the co-electrolysis combined with the Fischer-Tropsch reactions. So that makes the gasoline from those renewable sources. And other funds are also included in this fund. And also the recent interesting support is the Hydrogen Society Promotion Act. That supports the green hydrogen, making and using green hydrogen, but maybe companies will feel that the hydrogen price is too high. So the difference of the hydrogen prices of the green and other hydrogens can be supported by the government. That kind of the support has been recently established. And now, only very recently, 2 groups have been accepted. One is for green hydrogen from wind power making from the electrolysis, and for that is used for steel making. And also another one is the making ammonia from waste plastic to produce some ammonia related chemicals. And for this kind of support, the government provided 3 trillion yen, but for 15 years. And also Ministry of Environment supports several kind of the projects. So these are the rough sketch of the Japan's hydrogen projects. And I'd like to go to the high temperature solid oxide technologies. That is my favorite technology, and start from the what are SOFC and SOEC? Okay, SOFC is the solid oxide fuel cell. So solid oxide is the kind of these things. And so mainly used solid oxide is the zirconia. Zirconia is the used for electrolyte, because the zirconia conducts oxide ion. So it is a good electrolyte at high temperatures. So the crystal structure of zirconia is like this. It has the cubic fluoride structure, and zirconium 02 has this structure, but if you have yttrium 3 plus in the position of zirconium 4 plus, then the cubic structure is stabilized, and at the same time, oxide ion vacancy will be formed, because the yttrium 3 plus is only 3 plus, and zirconium 4 plus, that plus charge will be lost. So a negative charge, oxide O2 minus, is also lost to make the vacancy. So to have the electrical, the charge neutrality. So this is the electrolyte, and other parts are also made from the ceramics, conductive ceramics, and also nickel ceramics composite. We call it ceramics and metal composite, so CERAMET. So this is the SOFC, and how it works is in this video. I think this video works. Yeah, this is just a small demonstration about how solid oxide electrolyte makes the electricity. This is the solid oxide electrolyte, and the 2 electrodes are placed on both sides, and they are connected to this motor, and this is heated by using this burner, and then the temperature will go up, and at the same time, the oxygen on the upper side will be used for combustion. So the oxygen potential difference will be developed, and using that difference, it will generate electricity. So this is the solid oxide fuel cell. And why we use such strange fuel cell? Because it has a very high efficiency. So this graph shows the efficiency of electricity generation with heat engines. So this is gas engine, and this is for gas turbine, steam turbine, combined cycles, and the highest efficiency of about 63% has been already achieved by using this combined cycle. But if you decrease the size of the power generator, then efficiency goes down. That is the mechanical systems. But for fuel cells, even with a very small system, polymer electrolyte fuel cell shows 40% efficiency, and solid oxide fuel cell shows even higher efficiency, like 55% for very small 700 watt system. That is actually used for household cogeneration system. We call it NFARM. So it is SOFC operated, so it is NFARM type S. And recently, more higher efficiency NFARM is now developed by some company, Morimura SOFC company, and also some other SOFCs, including Bloom Energy for 100 kilowatt or more systems. That is, I think, very familiar to Korean people, because the Bloom Energy has the alliance with the SK, and they are selling very, large amount of electricity, this system. Anyway, fuel cell, especially solid oxide fuel cell, can generate very high efficiency. So even higher than the largest combined cycle for very small systems. And why can it generate high efficiency? That is based on the thermodynamics. So thermodynamics and kinetics. So if you are familiar to the thermodynamics of water formation, then you will think that the high temperature fuel cell is not as good as low temperature fuel cell in terms of efficiency, because low temperature fuel cell will have a higher Gibbs energy change. The Gibbs energy change is converted to electricity than high temperature system, because combustion of hydrogen to form water, this reaction reduces the number of gaseous species. That makes the entropy change negative. In that case, enthalpy change is almost constant, independent of temperature, but the Gibbs energy decreases at higher temperatures. And more higher temperatures, then it will go to negative, but it is very high temperature. It means that the water will spontaneously separated into hydrogen and oxygen at very high temperatures. But to go to the high temperature, gives the energy of water formation will somehow decrease in the absolute value. So people may think that the lower temperature system will give higher efficiency because higher power, but actually lower temperature system has higher overpotential. Overpotential is the loss of the potential or loss of energy to promote reaction in a practical rate. So high temperature systems has smaller overpotential, so we have the higher efficiency. And also for this higher temperature system, the exhaust heat, the heat comes from the thermodynamic equilibrium heat and also the in equilibrium heat generation from the overpotential, but both heat is generated at high temperatures. High temperatures heat, has higher quality than low temperature heat. So it can be used very effectively, especially when we use methane as the fuel. So if you use methane as a fuel, then the Gibbs energy change and enthalpy change are almost same, because the complete combustion of methane will not change the number of the gaseous molecules. So in a very ideal situation, it can generate electricity at 100%. But yeah, methane should be used first, reformed to make hydrogen, and then it is combusted in a fuel cell. But if this is done at high temperature fuel cell, then the exhaust methane reforming reaction is to make the hydrogen from methane using water vapor, and that is the endothermic reaction. That you need heat from somewhere. But if it is done with the high temperature SOFC system, the waste heat from the SOFC can be utilized very efficiently for the methane reforming reaction. So that is why we can have a very high efficiency with the SOFC. And also the kinetics. This is a typical IV curves, voltage current curves for the polymer exchange membrane fuel cells. And it has the overpotential for ohmic loss, concentration polarizations, and also activation polarization. Activation polarization is rather large for the lower temperature systems, but for higher temperature SOFC, activation polarization is very small. So in the polymer system, they will never get the theoretical open circuit voltage. But for high temperature systems, we always have the open circuit voltage that is the determined thermodynamically in a reversible way. So reversible system can be achieved at high temperature fuel cells. But if you compare these IV curves of high temperature system and low temperature systems, low temperature, especially polymer exchange membrane, PEM system, can generate very large current density. That is maybe the state of the art due to the state of art technologies made by many people. But anyway, current density rate, then they are comparable. But at rather low current density or around the open circuit voltage, solid oxide systems is much better. So they can have the pros and cons. So PFC, polymer exchange membrane fuel cell, is better for maximum power density, but for solid oxide fuel cells, it is better in terms of efficiency. So, and also the shutdown and startup capability is better for polymer exchange membranes or low temperature systems. For low temperature systems, fuel cells is usually used for vehicles. And for stationary generators, maybe high temperature systems is better. And that was for fuel cell. And for electrolysis cell, the situation is also the same, but more striking difference will happen because for electrolysis, in high temperature systems, you need only this part of electricity as the input power. And this another part for enthalpy is can be incorporated as the heat. So if you have external heat of high temperature, then power to enthalpy efficiency can exceed 100%. That is the high temperature system. But of course, to search for such high temperature heat, exhaust heat is not easy. So normally we use the overpotential that generates heat. So overpotential is if matched to the enthalpy value, then this electrolysis can be operated at thermoneutral situation. So in that case, we do not need high temperature heat, and we can generate electricity in reality basically it can generate heat at 100% efficiency. But of course, we have to input some heat, lower temperature heat, to generate water vapor. So if you have the water vapor, then the efficiency will be very high for high temperature systems. So these are the EU and DOE target for electrolyzers. And these numbers are kilowatt hour per 1 kilogram hydrogen, and alkaline or other low temperature systems have the similar values, but for high temperature systems, the value is very small compared to others. Now, of course, if you include the energy, heat in the total energy, then this difference will be much more smaller. But if you have the exhaust heat, then this it required energy for making hydrogen will be very small for high temperature systems. That is why we like high temperature system. And I almost used all the time, so I will skip. But these are the history of the development of the SOFC. It was first initiated by the Westinghouse, that is the US company, and then the first cell was in a tubular type, but then planar type cells were developed, and anodes, electrode supported cells were also developed. And then Kyocera developed the tubular, flattened tubular type, this one, and they are using this cell for household CHP systems. And now they are selling over 200,000 units. So I think that is the world's largest number of FC unit sales. And you know, the Bloom Energy has already sold the largest total capacity of fuel cells. So these are the stationary. And SOEC developments for all these situations, maybe the next talk will be more precise and better instruction for these current situations, so I will skip this one. And if we can achieve this technology, we can achieve the carbon neutral society using the hydrogen, also cogeneration system, so CO and hydrogen. Thank you very much for kind attention.
예, 다음은 한국재료연구원 풍력터빈기술연구센터 센터장님이신 박지상 센터장님께서 초혁신 경제 해상풍력 프로젝트 20메가와트급 초대형 해상풍력 터빈 개발 및 보급 계획에 대해서 발표해 주시겠습니다. 박수 부탁드리겠습니다.
안녕하세요. 예, 저 재료연의 박지상입니다. 저희 풍력 터빈기술연구센터 아니고 핵심기술연구센터입니다. 여기 어떻게 해서 그게 터빈기술연구센터로 바뀌었는지 모르겠는데, 예, 제가 오늘 말씀드릴 내용은 오늘 오전에 이 재생에너지 보급 관련해서 또 우리 중국과의 어떤 경쟁 관계, 중국이 다 이런 그 재생에너지 제조업 기반을 잡아먹는 이런 문제들을 막 많이들 말씀하시고 그랬는데, 특히 우리 윤희준 회장님께서 그렇지만 우리 이 에너지 관련 산업을 우리나라의 새로운 그 성장 동력으로 만들 수 있는 그런 기회가 될 것이다, 이렇게 말씀을 주셨습니다. 저도 확신하고 있거든요. 또 그런 말씀에 굉장히 공감을 하고, 그럼 그렇게 가기 위해서 우리가 뭘 어떻게 해야 되는지, 이런 게 굉장히 중요한 시점이 된 것 같습니다. 그래서 저희 태양광, 풍력 이런 분야들이 참 이런 시련을 많이 겪으면서 지난 15년 동안 사실 어렵게 여기까지 왔습니다. 저희가 기술적으로 부족하고 그런 건 아니에요. 근데 이 정책의 문제, 또 어떤 시장의 문제, 이런 것들, 또 어떤 경제적 논리, 이런 것들 때문에 무수히 많은 개발을 하고 좋은 기술을 갖고 있음에도 이게 산업으로 제대로 연결이 안 되고, 특히 우리나라 제조업으로 먹고 사는 제조업 기반의 그런 나라인데, 이 태양광이나 풍력 이런 게 우리 제조업을 육성 발전시키는 데로 연결되지 못하고 계속 이 좌절되고, 그런 거에 대해서 굉장히 이 분야에서 일하고 있는 분들이 상심을 많이 겪었습니다. 한 10수년 동안. 근데 이제 드디어 때가 왔다. 저는 이렇게 생각하고요. 오늘 그런 관점에서 이런 좀 설명을 드리고 싶고요.
감사합니다.
예, 고맙습니다.
좋은 주제 발표해 주신 센터장님께 박수 부탁드리겠습니다.
예, 세션 마지막 발표는 한국기계연구원의 김영상 책임연구원께서 고온 수준의 시스템 기술 동향 및 한국기계연구원 20kW급 시스템 장기 운전 결과에 대해서 발표하시겠습니다.
네, 안녕하십니까. 방금 소개받은 한국기계연구원 김영상입니다. 오늘 제가 발표드릴 주제는 고온 수전의 시스템에 관련된 전 세계적인 동향, 그 다음에 저희 연구원에서 최근에 수행한 이제 좀 연구 결과에 대해서 간략하게 소개를 드리도록 하겠습니다. 오늘 사실 이 내용들이 계속 많이 나왔던 것 같은데요. 넷째로, 그러니까 우리가 탄소 중립이라는 이야기는 지금 이제 피할 수 없는 시대적인 과제인 것 같습니다. 그리고 이것을 달성하기 위해서 우리가 이제 그러니까 화석 연료, 기존에 많이 쓰고 있던 화석 연료를 이제 대체할 수 있는 이제 새로운 에너지를 찾아야 된다라는 부분에서 이제 모두가 동의를 하고 있는 것 같고요. 그 중에서 가장 이제 우리가 당장 그리고 근미래에 우리가 달성 가능한 에너지로의 전환이 이제 수소가 되는 것 같습니다. 그렇게 해서 이제 청정 수소라는 이제 키워드가 넷째로 혹은 탄소 중립이라는 이제 키워드와 같이 지금 이야기가 되고 있는 상황입니다.